is a quick recap of thermodynamics chapter. Okay, where as the word suggests, the thermodynamics means thermo means heat, dynamics means movement, the flow of heat. A study with regard to the movement of heat is known as thermodynamics in simple words. Okay, so then you must be knowing that we are going to study particularly about ideal gas here. And in the ideal gas situation, you will only have kinetic energy, and the potential energy they'll completely ignore. The ideal gas, there's only kinetic energy. When the internal energy of any system is contributed by kinetic energy and potential energy. However, for an ideal gas scenario, we do not take potential energy into account at all. So this lesson is based only on internal energy, means increasing the kinetic energy of the system. So that is something you need to know. So then here comes the zeroth law of thermodynamics. The zeroth law is like this. This is imagine an A and a B, container A and B, which is separated by an adiabatic wall. And let's consider a container C. The in between of this is filled with diathermal wall. Diathermal. Adiabatic wall is like a flask or a wall which is not going to allow flow of heat from A to B. Okay, but a diathermal wall will allow exchange of heat. So A will exchange with C, B will also exchange with C. So then therefore TA is equal to TC. Temperature at A will be equal to temperature at C, and temperature at B will be equal to temperature at C. Therefore TA will become equal to TV. Okay, this is the zeroth law, where they say that the temperature is that physical quantity whose equality is a necessary condition for a system to be in thermal equilibrium. What is that? Temperature is that physical quantity, the keywords physical quantity, whose equality T is equal to TB means then the entire system we can call it is in thermal equilibrium. So temperature is that physical quantity whose equality is a necessary condition for a system to be in thermal equilibrium is the point that you have tried for zeroth law. So let's go to next. So next is about suppose you have a container which has got it's fitted with a piston. Okay, and there's gas inside. I'm going to heat it, or in other words, heat is going to be absorbed from the surrounding. You can either say you're going to heat it, or you can say you're going to absorb heat from this. You can also do that, right? So it's very hot, and sun's rays also you can absorb heat. So heat can be absorbed from the surrounding. Either ways, it will increase the internal energy of the system. தண்ணி சூடு பண்ற மாதிரி தான் அந்த குட்டி குட்டி பாயில்ஸ் எல்லாம் வருது, which means there's an internal energy is rising. Apart from that, the piston will also get pushed up when this happens, which means that shows that the heat supplied, which is delta Q, goes about in increasing the internal energy of the system, which is delta U. And other than that, it's also doing some work. Let's see, this is supposing move through a distance delta X, and this is area of cross section A. The change in the volume is A into dx. Okay, and therefore the work done, work done is P into delta V. P into A into dx. This is the work done. So work done itself is force into displacement. Force itself is pressure into area into displacement, and thus this becomes your dW, or the work done. So then the energy supplied or the energy absorbed goes about in increasing the internal energy system, and the system doing work on the surrounding. System is pushing the piston up. You can consider the piston to be the surrounding. So the energy supplied or the heat supplied goes about in increasing the internal energy system, and also doing the system doing a work on the surrounding. So this is known as first law of thermodynamics. First law of thermodynamics. So then this statement is very important. And after that, we have to do a PV graph. This is called indicator diagram. Indicator diagram, where when the pressure is increased, the volume decreases. So then the graph goes like this, like a reciprocal function. And the area, P into this itself is P into delta V. I forgot to tell you. Delta Q is equal to delta U plus P into, this is nothing but A into dx, which is change in volume. So this is the final statement, and the fact that the work done is nothing but P into delta V shows that you can take a small area under the curve, which is dV, and the area under the curve will be P into dV integrated from volume 1 to volume 2. That can also be the work done. So that this is the indicator diagram. The fact that the pressure is increasing, the volume is decreasing, so that it's compression, and if it's going to be in this direction, it's going to be expansion. So that is the indicator diagram. So after this it is about these numericals, which are very, very important. You have a numerical with if you see aurora, you have a pressure, atmospheric pressure, ATM, and the volume, which is in liters, and there's a graph which has been given to be some kind of a rectangle here, where this point corresponds to 1, this point corresponds to 4, this point corresponds to 2, and this point corresponds to 5. So 0, 5, and this is 0, 2, and 1, 0, and 4, 0. It's been given that this pressure and volume, unlike in the mathematics, we'll write 0, 5 and 1, 0 and all that. This is not mathematics. Not like mathematics. You are doing a PV graph. This is a PV graph. The coordinate will also be PV only, which means you're writing the y coordinate first and then writing the x coordinate for a change. That's a very important point you should understand. So then, therefore, this area under this area inside this will give you the work done. Correct? Because it's a cyclic process. Can you see where it started? It ended there. This is called cyclic process. If you want to find the area under this, it's just, let's name it as A, B, C, D. Can you imagine this to be area under AB completely minus area under DC? Will give you area of the rectangle, from which, in this case, I can just infer the area of the rectangle and do it, which is length into breadth. And what is length is this, which will be your this distance is change in volume, which is only 4 minus 1, which is 3, and this breadth will be 5 minus 2, which will be again 3. So 3 3s are 9 square. 9 square. What is it? 9 is the work done. Okay, but you know this is in atmospheric pressure and the ATM, and this is in liters, and you have to write it in. Okay, so you have to work done. You get this answer, which is P into delta V, which is in ATM. To convert 1 ATM, it's 1.013 into 10 to the power 5 Pascal. That will give you SI unit, and the volume is in liters. And you should know 1 liter, which is like the 1 liter of milk that you get outside your house every day morning. Can you imagine that to be 10 centimeter cube? 10 by 10 by 10, we can imagine like that. Okay, that's the, so 1 liter is equal to 10 centimeter cube. Correct? Then the question will be about 1000 liters. 1000 liters is like a big water tank full of milk. Can you imagine? That will be like a 1 meter cube. 1 meter cube. And so this is the conversion. So when you convert the volume from here, we are converting from liters to meter cube. Okay. Oh no, they are converting it to erg. They are converting it into erg, which means I should not have pressure in Pascal, which means I can't write pressure also in Pascal. If I'm converting it to SI unit, fine. But they didn't specify anything. But you can always convert it into SI units and do the sum. So about what they have done is just converted it into erg, because pressure itself is force by area. So it's force by area. No, work done. Work done itself can be in erg, and how to get an erg answer here? This can be written 1 liter is 10 centimeter cube. So that's sorted. And the pressure, CG's unit of pressure is, let's see, it's 3 into.
No, it's 10 power 6.
3 into 10 to the power 6. Where have they specified that? And AD is 3 into 10 to the power 6 dyne per centimeter cube. Dyne per centimeter cube.
This 10 power 3 is for the volume.
Okay, let's convert into SI unit. That's easy for us. Okay, let's convert this pressure, which I've written, is in multiplying by 1.013 into 10 to the power 5. And let's convert the liters into a meter cube. Liters, 1000 liters is 1 meter cube. The question is only about 3 liters, right? Is how many? So you can just inform from there. It's going to be 3 into 10 to the power minus 3 liters, correct? So then therefore it's 3 into 10 to the power minus 3 liters into what was the other pressure? We have to multiply it with 1.013 into 10 to the power 5. So you'll get some other answer which is different from that, but I'm not converting it to CGS. For me, it's what is convenient is to do it in SI. So let's go to the next question. And the whole most important point that we should note down in all this is a PV, not the usual x coordinate comma y coordinate. That's something you need to know. This is atmosphere, and this is V again in liters. They're given this to correspond to 1, this is corresponding to 3, this corresponds to 0.2, this corresponds to 0.5. Normally, if you have to find this, it's just the area of what the inside portion, but they will name it as A, B, C, D. They'll find the area under AB, and then they'll find the area under DC and subtract. You don't have to do that. You can just find the area of ABCD, which itself is like a rectangle. What is the difference? This is 2 and this is 3. So it's 2 into 3, but again we'll be getting answers only in SI unit. Yeah, they are also done it in SI unit. They seem to have done it in SI unit. The same thing that I have done. So you know what to proceed. You can do it 2 into 3. 2 is volume. It's 10 to the power minus 3. And this is the pressure, which is 3 into 1.013 into 10 to the power 5. That will give you in answers in joules. So that completes the sum. So like this, if they ask you any, these are all cyclic processes, and it's very easy to find the work done under it. So then, as I told you, first law states that the heat supplied goes about in increasing the internal energy of system, and also the system doing work on the surrounding. So this is the thing that you should understand, and we got numericals using that. So see, I'll just do 2 numericals for you to understand. Not much will come from this chapter, but these are very important for entrance exam. 1 gram of water at 100 degrees Celsius. Okay, 1 minute. I'll just teach you what is the meaning of latent heat and specific heat, which is very important. The word specific heat and latent heat is very, very important. Specific heat is the amount of heat, delta Q, which is supplied to a body to raise its temperature by delta T. Okay, it's Q is the amount of substance, amount of heat supplied to raise the temperature of the body by delta T. That is 1 gram of a substance. So this mass, it may be 1 kg of a substance, maybe 1 gram of substance. It can even be 1 mole of a substance. So then whatever that substance unit is into delta T. So dQ will be proportional to M into delta T. dQ will be equal to C into M into delta T, where this proportionality constant is known as specific heat. And specific heat is C is equal to delta Q by M into delta T. As you know, this is in joules per kg per Kelvin. Joule per kg per Kelvin, correct? Specific heat unit is joule per kg per Kelvin. That will be the SI unit of specific heat. This happens when there's a change in delta T. Change in delta T. That is when you're taking the water, it is at room temperature. You're going to heat it. The temperature will go from 30 degree to 100 degree. So there's a change in the temperature. During this process, the proportionality constant is called specific heat. But do you know that as I boil the water, once it starts boiling, it started to boil. Once it started to boil, if you have a thermometer fitted in both the cases, here there's an increase in temperature. But once it starts boiling, until all the water evaporates into vapor, it will continue to show only 100 degrees Celsius. Do you know that, right?
Why only 100?
It will always be 100 until the entire water disappears and becomes vapor. That's called latent heat. Okay, so I'll tell you what, in spite of the fact that you're heating, there is no change in the temperature. Correct? In spite of the fact, and this comes only when there is a change of state. Here there's no change of state. When there's no change of state, there's a conspicuous increase in the temperature, and the specific heat is the constant involved. But here there's a change of state, and so then there will be no, until all the water evaporates and becomes vapor, the temperature is going to remain to be 100 degrees Celsius.
This is for latent heat.
That's known as latent heat. So then here delta Q is proportional to the mass of substance, but no delta T. Okay, so then delta Q is equal to L into M, where the L is nothing but the delta latent heat, which will be joule per kg only. So whenever there's a change of heat, what is involved is latent heat. Okay, change of state. Do you understand this? This basic is very important so that you can learn those sums. Like 1 gram of water at 100 degrees Celsius is converted into steam. So then latent heat is involved. Very good. So it involves latent heat because it's converting into steam. You know that there's 1 gram of water. And the moment I read it, I want the volume. I don't want gram because I need this change in volume and stuff. Okay, I also need the grams part of it. Okay, we'll come to that later. 1 gram of water at 100 degrees Celsius is converted to steam at the same temperature. The volume of the steam is 1671 centimeter cube, which is volume of the steam is 1671 into 10 to the power minus 2 the whole cube. That is the volume of the steam. Are you clear? Now, what was the volume of the water initially is 1 gram. Let's convert and find the volume. You know, density is mass by volume. Volume is mass by density, and the mass is 1 gram by density. Let's convert gram into kg. So 1 into 10 to the power minus 3 by density of water is 10 to the power 3. So when it goes up, it will become 10 to the power minus 6 in SI unit. So therefore the volume of the water originally was 1 into 10 to the power minus 6. This is 1671 into 10 to the power minus 6. So therefore you can find the change in volume, which is subtraction 1671 minus 1, which will be 1670 into 10 to the power minus 6. You found the delta V. Because the whole question will be find the internal energy of the system. You know, like the first law, delta Q is equal to delta U plus P into delta V. The internal energy therefore is delta Q minus P into delta V. This is the internal energy. That's what they're asking you to calculate. And delta Q itself is nothing but L into M, because here it is the latent heat. So L into M minus P into delta V. L is nothing but they would have given latent heat is 2256 joule per gram. They are giving in SI unit. 2256 joule per gram means we need 2256 divided by 10 to the power minus 3 to convert the gram into kg. So it's 2256 into 10 to the power 3. So that will be standing for latent heat 2256 into 10 to the power 3 into mass of the substance. You know, it's just 1 gram initial mass. That's what you're heating. Okay, minus pressure is 1.013 into 10 to the power 5 into.
Shouldn't we write this gram and kg?
Which one?
This
Oh,
one.
I didn't. Sorry, it's 10 to the power minus 3 kg. So the gram into kg. So this and this gets cancelled. Excellent. P into delta V, where delta V itself is 1670 into 10 to the power minus 6. You can always solve this and write the answer. This and this is just 10 to the power minus 1. And then take it in, it become 167 into 1 point whatever, and then subtract and write the answer. You are supposed to get an answer which is 2086.829 joules. That will be the internal energy of the system. So energy basically is in joules. So yeah, so do you know that we can even convert, you can even have the heat in terms of calories. It need not be in terms of joules, and 1 calorie itself is 4.2 joules. Do you know this conversion? 1 calorie is 4.2 joules. You don't know?
I studied some.
Okay, just remember that. So then the calorie is a larger unit. You can convert into joules if you need it, but SI unit is always only in joules. However, we have calories to be another unit. Okay, so they give you in calories, you have to convert into joules. They won't ask you much from this. It's just for your knowledge. I'll go to next this sum, which involves at 0 degrees Celsius and at normal pressure, the volume of 1 gram of water increases from 1 centimeter cube to 1.091 centimeter cube. This is water and this is ice. It's freezing, which means, see, in this process, heat is getting absorbed. So delta Q can be positive. In this process, the heat is getting released. So you should write minus delta Q is equal to delta U plus P into delta V. That's the only change. Are you clear? So then 1 centimeter cube is converting to 1.091 centimeter cube. So then the delta V is directly there for you. You don't have to convert anything. You just, oh, it's in centimeter cube, convert it into meter cube. So 1 into 10 to the power minus 2 the whole cube. This is 1.091 into 10 to the power minus 2 the whole cube, which will get you minus 6. You can subtract this and this, you get delta V to be 1.090 after subtracting these two.
Ma'am, they have given it in the question, ma'am, that heat is released.
No, that is something we need to know.
How did it?
When you, something is getting frozen,
Oh, okay.
it will obviously release heat. So then therefore the delta Q becomes negative. So those are the sign conventions which you should know. So then this becomes your delta V and your pressure is 1 point. Okay, you are finding what is delta U. So this will go that side. So delta U thus will become minus delta Q minus P into delta V. Correct? And you can find, and what is the answer? The answer has to be negative. No wonder both of them are. This involves again at 0 degrees Celsius. Until all the water freezes into ice, or until all the ice freezes into water, it's going to remain as 0 degrees Celsius. So latent heat into M minus P into delta V. You know delta V from here, you know pressure 1.013 atmospheric pressure. Latent heat value of fusion, that is known as latent heat of fusion. This is known as latent heat of vaporization. The latent heat that was specified in this is latent heat of vaporization. But here it's freezing. So latent heat of fusion. They would have given you latent heat of melting ice is 80 calorie per gram. I told you how to convert a calorie joules. For one calorie is 4.2 joules. So 80 calories, how many joules you can convert, and grams also should be converted into kg. And then it's question of substituting here. And what was the original mass of, original mass is 1 gram of water. You can substitute that as 10 to the power minus 3 and do the sum. The answer for this should get you, okay, they are writing in calories, so I can't compare this, my answer with that answer, but you understand how to do this. Okay, so then comes the next thing is Mayer's formula. So you understood what is the C means. P means specific heat, which is delta Q by M into delta T. Latent heat means L is equal to delta Q by just M. So that should be enough for this exam. They won't ask you much from this chapter, but for the derivations. Okay, so then next is Mayer's formula. I'll teach you Mayer's formula. Write the first law. Sorry, first law is delta Q is equal to, 1 second, hold on. We know from the first law delta Q is equal to delta U plus P into delta V, and this forms the basis for us to go forward from here. Okay, so supposing we are going to study this entire thing at constant volume. Constant volume, we're going to do a study. Delta V will not be there. Therefore, this will get cancelled. Correct? So you get delta Q is equal to delta U at constant volume. Correct? And let's divide both sides by delta T. Okay, change in temperature. So delta Q by delta T at constant volume, so suffix it with volume, becomes equal to delta U by delta T, which itself is nothing but, for considering one unit mass, the M to be just a unit mass, you know this itself is CV. Yeah? CV is a specific delta Q by M into delta T, but M can be considered as unity, and so this. Therefore, this is your first conclusion. Now let's take the same statement, delta Q is equal to delta U plus P into delta V, and study under constant pressure. So under constant pressure, what will happen? Under constant pressure, so nothing will happen. So you just have to divide. This is the statement, because everything will be valid. Under constant pressure, nothing is getting deleted. P is a constant, that's all. So you have to divide everything by delta T. Delta Q by delta T is equal to delta U by delta T plus P into delta V by delta T. And this itself is under constant pressure, which will give you a CP, specific heat at constant pressure. Okay, but now what you should do, mark this as your equation 2. But this itself is CV, delta U. Can you see?
Yes.
So then therefore CP is equal to CV plus P into delta V by delta T. You take this gas equation, PV is equal to nRT. I'm sure you know this equation, right? R is a gas constant, and N is the number of moles, and P pressure volume. So suppose you're going to differentiate at constant pressure, P is a constant. So when you differentiate P into delta V is equal to N into R into delta T. This is a change in temperature alone. Okay. So then from here you can consider N to be 1 mole and ignore it. So then instead of P into delta V, you can also write R into delta T. So what happens? Cp is equal to Cv plus R into delta T by delta T. Delta T get cancelled. This R, which is a gas constant, is Cp minus Cv. So if they give you Cp, you know the gas constant, you can add it with Cv and stuff. Okay. R itself is gas constant, which is 8.3 joule per mole per Kelvin. It's a gas constant R. Okay. So do you understand? If you know Cp, you can find Cv. If you know Cv, whatever that is, you can find. That's what they have done. They might sometimes give you ratio of Cp by Cv, but you can always write Cp in terms of Cv. You know this, and then you can solve it. Very easy. Okay. So next thing is the isothermal process. Isothermal process. As the word says, iso means one temperature, constant temperature, which means, see, if I have to maintain your body at a constant temperature, I should enable you, supposing you become cold, you should be able to absorb heat from the surrounding. If you're becoming hot, you should be able to release heat to the surrounding so that your body can be maintained at a constant temperature. So anything done at a constant temperature means exchange of heat is allowed. The word constant temperature makes it clear that exchange of heat should be allowed. It's possible. So then you take a container which consists of gas, say you have a piston attached to it, and you're going to do isothermal process. In an isothermal process, so then here it is considered an ideal gas enclosed inside a cylinder provided with the piston having conducting walls. Point number 1. Why? Because it should allow flow of heat with the surroundings. So conducting wall. If the gas is now slowly compressed, the process has to happen slowly, because apada the heat exchange with the surrounding will happen. If you do something swiftly, that will not happen. So the process has to be very, very slow. You're going to compress the gas and you're going to do it slowly. Then what will happen when the gas is compressed? Its kinetic energy, internal energy increases. In the internal energy increases, the temperature also increases. Okay, when the temperature increases, it has to release the excess temperature heat into the surrounding. So it has to be transferred to the surrounding when you're compressing. And we are expanding. The internal energy decreases, so temperature change decreases, and so then you have to absorb heat from the surrounding. So that is this point that I have given, and this is an isothermal process, and they are studying this. Okay, and what are the key points? One is they should have a perfectly conducting walls. The process has to be very slow, and okay, that's all. Okay, and PV is equal to nRT. Let's take a gas equation. Here T is going to be a constant. R is a constant, N is also constant. So PV is equal to constant is the conclusion. The gas equation is becoming like this. So that's the last point. Okay, and this itself is Boyle's law. Boyle, a scientist, said P is inversely proportional to V. That PV indicator diagram is nothing but a Boyle's law at constant temperature. Okay, at constant temperature. So then you understand, sorry for the bad handwriting, but you'll understand because I'm teaching you here. So then that completes it. That completes the isothermal process, right, to note on. Okay. Next is, okay, work done. We're going to derive a formula for work done in isothermal process. Isothermal process. So the work done itself is P into delta V. We have learnt it now from V1, integration from V1 to V2. Just write this formula, and then PV itself is a constant. So PV is equal to nRT. So you write what is P from here, nRT by V. Take it and substitute here, nRT by V into delta V, where nRT is a constant. An integration of 1 by V will be ln V or log V to the base E, or we'll write ln V. Okay. So log, you can convert log, okay, integrated from V1 to V2. So then upper limit minus lower limit, log V2 minus log V1, but both of them with a base E. So it's nRT into log of V2 by V1 but to the base E. You don't want a base E. Our clock tables are based on the base 10. So then therefore 2.303 nRT, you have to multiply with this constant, so that becomes log of V2 by V1. You know PV is a constant, which is P1 V1 should be equal to P2 V2. So P1 by P2 is equal to V2 by V1. Therefore this can be also written as 2.303 nRT log of P1 by P2. So this is the work done in an isothermal process. They might ask you this as your derivation. Next is adiabatic process. This is the most important. There's no paper without the derivation for adiabatic process. So adiabatic process, as you know, that there is no flow of, no exchange of heat with the surrounding. No exchange, which means you should have an adiabatic wall. It's a non-conducting, a perfectly adiabatic wall or a non-conducting wall, and then you have a piston attached to it, and here there should be no exchange of heat with the surrounding. So consider glass enclosed cylinder, ideal gas, having perfectly insulated walls, and you have to do this process very swiftly. So the next point is you have to do it so quickly so that there is no exchange of heat. The work, so you are allowing it to expand very quickly. So you're going to expand it this very quickly. The work is done by the gas during this expansion. So it's, you know, when you expand, the internal energy always decreases. When now internal energy decreases means temperature also decreases. As no exchange of heat is allowed, the temperature really falls. So delta T is there in this. In the previous one, the delta T wasn't there, but here there is delta T. Okay, so similarly, when the gas is suddenly compressed, you know, the internal energy increases, the temperature increases with no transfer of heat, so there is obviously a delta T. Correct? So then that's the point you must write. And so what are the adiabatic wall, and swiftly, and you are allowing it to expand and compress, and no exchange of heat is allowed. And in this process, since there's no exchange of heat allowed, you're going to derive write the delta Q is equal to delta U plus P into delta V. Okay, so then let's write what happens to gas equation here. You know, PV is equal to nRT, where T is also variable. You have to do a derivative for that also. So it's U and V. So P into delta V plus V into delta P is equal to NR into delta T. It's differentiated as U and V. So this is something that you have to take into consideration while doing adiabatic process. So the gas equation thus changes like that is the conclusion. So coming back to delta Q is equal to delta U plus P into delta V. You know, there's no change of flow of heat. So delta Q becomes 0.
Yes.
So then it's equal to delta U plus P into delta V. Now you should know that what is delta U. We just saw from Mayer's formula, at constant volume we found CV is equal to delta U by delta T. So delta U can be written as CV into delta T. So 0 is equal to CV into delta T plus P into delta V. Correct? And now take PV is equal to nRT, this equation that we found. You know, and take this again and do it. nRT, consider N to be just 1 mole, it's okay. And then you're going to differentiate this. So P into delta V plus V into delta P is equal to R into delta T. From this you write what is delta T, because we're going to substitute for this delta T. So it's equal to P into delta V plus V into delta P by R is your delta T. So let's substitute. 0 is equal to CV into P into delta V plus V into delta P by R plus P into delta V. Let's take an LCM, which will be R, and R goes, that it will become 0. So now you bring this in, you get 0 is equal to CV P delta V plus CV V delta P plus R P delta V. Take this equation and consolidate P and P. So 0 is equal to P into P delta V can be taken out. P delta V is common, you get CV plus R plus CV into V into delta P. But from Mayer's formula, you know, Cp minus Cv is equal to R. So Cp is R plus Cv. This can be replaced as Cp. So you get 0 is equal to P into delta V into Cp plus Cv into V into delta P. Now you should divide this by Cv, C suffix V, Pv, C suffix V, Pv. So Cv, Cv get cancelled, V and V get cancelled. You get delta P by P, and here you get P and P get cancelled. You get this as Cp by Cv into delta V by V plus a delta P by P. Cp by Cv itself you should know is a constant always, which is given by gamma, is equal to delta V by V plus delta P by P. Now integrating both sides. Integration of 0 is a constant. Okay, so when you integrate this 1 by V dV, it will be log V. It will be ln V, but here they are using straight away log, they don't use 2.303 and all. Okay, log V plus integration of this will be log P. This property, which is a log of x to the power n, can be written as n log x. Or the கொண்டையில் இருக்கிறது மண்டையில் கொண்டலாம் இல்ல மண்டையில் இருக்கிறது கொண்டையில் கொண்டலாம் funny சொல்வேன், so that children can remember. So this gamma can be brought to the power. So log v to the power gamma plus log p, and this addition becomes multiplication. So log p v to the power gamma is a constant, and there's this property like log x to the base e is equal to t, e to the power t becomes x. Okay, e to the power, you know this property?
No.
Okay, so then just consider this all is to the base e, right? So e to the power k will be equal to pv to the power gamma. Using this property, you should know log x to the base e is equal to t, e to the power t becomes x. That is, any exponential function can be converted to logarithmic, or logarithmic can be converted into exponential like this. So then therefore e to the power k is equal to pv to the power gamma. E to the power k itself is a common constant, so pv to the power gamma is a constant. It's not PV a constant, it's PV to the power gamma is a constant in the adiabatic process. You know then PV is equal to nRT. You can write, ignore the n, and you can write V is equal to RT by P. Substitute that here. P into RT by P the whole to the power gamma is a constant. P to the power 1 minus gamma into T to the power gamma. Let's forget about the R also. Ignore all that. Okay, so P, because this can come down and it still becomes a constant. So P to the power 1 minus gamma into T to the power gamma is a constant. This is the second conclusion that you get. Similarly, you can also substitute for P from this. P is equal to RT by V. Substitute that in this equation. P itself is PV to the power gamma is a constant. RT by V into V to the power gamma is a constant. So R can be brought and you can write as constant. This is T V to the power gamma minus 1 is a constant. This is third important because they will have numericals based on this, and this is very important. And so whether they're going to ask you this or they're going to ask you the work done in an adiabatic process, we don't know. So next is work done in an adiabatic process. Anything can be your question. So work done in an adiabatic process, you know that work done is always P into delta V. So you start always, work done means it's work adia. That was work isothermal. Iso, you read W iso wherever we did previously. Here it's iso. This is adia, where the work done itself is integration of P into delta V. Correct? But you know PV to the power gamma is a constant. So write P from this is K by V to the power gamma. So when substitute that, it will be K by V to the power gamma into delta V, where K can be taken out and V to the power minus gamma into delta V. So K into V to the power minus gamma plus 1 by minus gamma plus 1. You know x to the power n is x to the power n plus 1 by n plus 1. Do you know integration?
No. Yes.
You know x to the power n is x to the power n plus 1 by n plus 1. Yeah?
Yes.
So then you write it like this. This will be your gamma. This will be your V. Correct? V
minus 1.
Yeah. So then upper limit minus lower limit is V1 to V2. So K into V2 to the power minus gamma plus 1 by minus gamma plus 1. Or can I write it as V2 to the power 1 minus gamma, doesn't matter, by 1 minus gamma minus V1 to the power 1 minus gamma to the power 1 minus gamma by 1 minus gamma. Write it like this. Now what you should do is, you know, K by 1 minus gamma itself is a constant. So V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. Now what is K? You know, PV to the power gamma is a K here. So you can take the K inside, 1 by 1 minus gamma into PV to the power gamma. P2 V2 to the power. Change it accordingly. P2 V2 to the power gamma into V2 to the power 1 minus gamma minus the K is brought inside. So P1 V1 to the power gamma, V1 to the power 1 minus gamma. So when you consolidate, this will be V2 to the power P2 into V2 minus P1 into V1. So they will, for some reason, they'll write it as gamma minus 1 and interchange this. So P1 V1 minus P2 V2. And you should know that PV is equal to P2 V2. And you know that PV is equal to PV.
NRT.
Generally PV is equal to nRT. So you can write this as nRT1. nRT1 minus nRT2. Here alone we are using general. We are not using PV to the power gamma. So then it's 1 by gamma minus 1. So nR can be taken out common. A gamma minus 1 is into T1 minus T2. These are all the various ways in which you can work on. Both of these derivations that I did in adiabatic is very, very important. Play it again and again and become very thorough. So that's the thing. And there's lots of numericals that can be asked based on that. So then let's look at one of the numericals. The compression ratio of a certain diesel engine is 15. Compression ratio means volume is getting reduced. So a V1 by V2 is equal to 15 is what is the compression ratio mean. This means that air in the cylinder is compressed to 1 by 15th its original volume. Okay, so then the V2 is 1 by 15 of V1, where V1 is the initial volume. Okay, if the initial pressure is 1.0 into 10 to the power 5 Pascal, which is the atmospheric pressure, is the initial pressure, and the initial temperature is, they are saying 300 Kelvin. If they don't give in Kelvin, they give you in Celsius, you have to convert plus 273 into Kelvin. Okay, and then pressure itself is 1.0 into 10 to the power 5 Pascal. Find the final pressure and the temperature. So this is initial P1, initial temperature T1, and the volumes ratio is like this. Okay,
P1 V1 is
you know that okay, this is the relationship between P1 and V1. P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Okay, so then you know P1. You can write V2 in terms of V1. So P1 V1 to the power gamma is equal to P2 into 1 by 15 to the power gamma into V1 to the power gamma. So then V1 to the power gamma will get cancelled. You know the initial pressure is this, you can substitute, hence you can find this, provided they give gamma. The gamma, they should give it beautifully, otherwise we can't do. In this sum, the gamma has been given as 1.4. See, when they give you as 1.4, no, it's very hard to do it, because it is 1.4 is like 7 by 0.2, 0.7 by 2. No, 7 by 2 is what? No. What is 1.4 by 10? 14 by 10, which is 7 by 5. Okay, you can't solve a 1 by 15 whole to the power 7 by 5 without a clock table. And we are not allowed to use the clock table in the exam. So then they will give you in such a way that it will be like, no, it will be 3 by 2. 1 by 16, say, for example, the whole to the power 3 by 2. You can write as 1 by 16, the whole to the power 1 by 2, the whole cube, which is 1 by 4 to the power 3. So you can do such sums, but the numericals have to be replaced. But the idea behind the sum, do you understand? The logic behind it. So then to find the temperature, you should go for the T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. Now that you know the relation between V2 and V1, substitute, then you know T1 is 300 Kelvin, hence you can find T2. So that is where all this is useful. So when they give you sums like this, you can manage and do. So I don't have to continue with this. Yeah, then comes this sum here. I don't think it will come down. This much will do. Are you clear?
Yes,
Heat engine is not there for you, and even second law and third law has been omitted for you guys.
Second law, we wrote it in the class.
You wrote it, so I'll also write it. What is second law? Okay.
Only the definition.
Okay, you should know that second law has got Kelvin-Planck statement. This is one statement, and there's one more statement which is Clausius statement. What is the Kelvin-Planck statement? It's impossible to construct an engine which will produce no effect other than extracting heat from the reservoir and performing an equivalent amount of work. You didn't understand anything from reading this. I'll tell you what. You have a reservoir, steam engine. Inga coal irukku. The coal la erinji you get the steam with which the train is able to run. It's not possible for any engine to completely convert the heat absorbed into work done. There will be some amount of wastage, heat loss. So that's what it means. It's impossible to construct an engine which will produce no effect other than extracting heat from the reservoir and performing an equivalent amount of work. It's not possible to do that. That's the first statement. So the next statement is the Clausius statement. It's impossible for self-acting machine, unaided by any external agency, to transfer heat from a body to another at a higher temperature. A lower temperature to a higher temperature. Is it possible the heat flows always from higher to lower? Normally heat flows from higher to lower. Can the heat flow from cold to hot bodies? No. So you need an external agency to perform that. So that's what it is. It is impossible for a self-acting machine, unaided by an external agency, to transfer heat from a cooler body to a hotter body, or a body at a higher temperature. Are you clear?
Yes.
The best example is food kept in the fridge. அந்த ஒரு ஃபுட்டு ஃப்ரிட்ஜுக்குள்ளே ஃபுட்டு வச்சுருக்கேன். அந்த ஃபுட்டு வந்து ஏன்னா கொஞ்சம் கொஞ்சமாக டெம்பரேச்சர் வந்து ரைஸ் ஃப்ரிட்ஜுக்குள்ளே வைக்கும்போது முதல்ல கூல் ஆயிடுச்சு. So it's now gone into that temperature of the fridge. But what happens is, over a period of time, slowly the temperature will start rising.
Oh, yes.
So that temperature heat has to be transferred to the surrounding. Surrounding is like a coolant will be there. That heat will be passed on to that tube which contains a coolant. And so constantly you can maintain the food at a constant temperature. And where there is a heat flow from the cold body also to a hot body, and that is the Clausius statement. So I'm done with this lesson. The Carnot engine has been omitted for you, so I don't have to do it, okay?